Introduction to Motion, Building the Physics Toolkit.
Hey everyone, welcome to another explainer. We're looking at something absolutely fundamental to our physical reality. We're talking about how we measure, describe, and literally map out motion. We're going to unpack the language of physics that lets us understand everything from, a casual walk in the park all the way to a rocket launching into space. It's all about motion, but more specifically, it's about giving that motion actual meaning.
Okay, I want you to picture this for a second. You lace up your running shoes, you step out your front door, and you run a grueling, exhausting 10-mile loop around your neighborhood. You are pushing yourself to the absolute limit, and eventually, you stop right back on your own front porch. Now, here's the puzzle. Physically, you just moved 10 miles, right? You put in the work. But in terms of your actual position in space compared to where you started, did you actually go anywhere? Well, the answer to that question completely changes depending on whether you're using everyday language or the highly precise language of physics.
Scalar quantities, magnitude only. A scalar quantity is defined as physical quantities that require only magnitude, which is a numerical value. And the absolute key phrase here follows right below that: direction is not required. Scalars are all about the how much or the how big. They're just pure values. They really don't care about the which way.
The crucial point is that when you're dealing with a scalar, once you have the number, boom, you have the complete picture of that measurement. Adding a direction to a scalar wouldn't just be unnecessary, it would actually be total nonsense.
Think about it for a second. If you ask me how long a movie is, and I tell you 2 hours, well, you have all the information you need. That's time. If I said, hey, the movie is 2 hours to the north, you'd look at me like I'd completely lost my mind, right? Time doesn't have a direction. And the same goes for distance. If a track is 400 meters long, that's a complete physical description of the track's length. It is a pure scalar quantity.
And that brings us to speed, which our notes also list as a scalar. Speed is just how fast you're going, say 60 miles per hour. But what happens if you're an air traffic controller? Knowing an airplane is going 500 miles per hour just isn't enough. You desperately need to know if that plane is flying north, south, east, or west. Just knowing the scalar, the speed, isn't sufficient in that case. You need something way more robust. So let's move on and see how this builds into our next core concept.
Vector quantities, adding direction.
A vector quantity is defined as physical quantities that require both magnitude and direction. And I really want to put strong emphasis on that word "and." You literally cannot have a vector without a direction. If you drop the direction, it basically ceases to be a vector and reverts right back to being a simple scalar.
Vector equals magnitude plus direction. It's just a simple, elegant formula. You have the how much, which is the magnitude, plus the which way, which is the direction. Vector quantities are displacement, average velocity, and average acceleration. Let's go back and remember our 10-mile run from the very beginning of the explainer. Your distance, the scalar, was 10 miles, but your displacement, which is a vector requiring direction, was actually 0, because your overall change in position from start to finish was, well, nothing. You ended up right back exactly where you started. And just like we talked about with the airplane, velocity isn't just 500 miles per hour, it's 500 miles per hour due east. That direction literally changes everything.
Describing motion 4 ways. Translating the physical world.
So okay, we have our quantities, our scalars, and our vectors. But how do we actually communicate these measurements? Physicists translate this physical reality into usable data. Motion can be described using words, numbers, equations, and graphs. And this is a complete translation toolkit. We can talk about motion in a sentence using words. We can assign it numbers like 60 miles per hour. We can plug it into equations to predict exactly where an object will be in the future. Or we can plot it out on graphs to visually track a journey over time. Whether it's a scalar or vector, we have these 4 distinct ways to describe its motion to the rest of the world.
And I want to leave you with a final thought to chew on. Yes, these are principles of physics, but they apply to so much more. Think about the energy you expend every single day. Are you just moving fast, generating a ton of speed, but running in circles like our 10-mile jogger? Or do your actions actually have direction? Are you truly moving forward? In your own life, are you measuring your progress in speed, or are you measuring it in velocity? Thanks so much for joining me for this explainer, and as always, keep exploring.